Alright, hi everybody. Welcome to Electric Circuits. So today's going to be a lot. Today's going to be me trying to really quickly review all of the ideas, all the topics in circuits. So we'll see how it goes. Circuits is a long unit. It's really complicated. So we'll see what happens. So what I'm going to do is do this review lecture, and then hopefully it'll be kind of short, and then I'll be able to give you some conceptual practice questions. If it's not short, then I won't give those to you. I'll post them probably, but I won't be like, hey, do this. This is due. Because I want you kind of, looking at this, getting the ideas down. So this is pretty much it for us, which is crazy. The AP test is going to be on Wednesday, May 13th. We'll have a little magnetism review on Tuesday maybe. I don't know what I'm thinking, but I'll be around on Tuesday to answer any last minute questions via Zoom. And yeah, so we're going to get into it. So we talked about yesterday or 2 days ago about this idea of potential difference. And this idea of potential difference is huge because we can use it to our advantage. This idea that charges kind of have this energy that's associated with moving them through an electric field, that's huge. So we do this all the time with batteries. So with batteries, we have these chemical processes. We don't have to know about how it works, but they create a potential difference by having a positive end and a negative end. So you have these ions that are separated chemically within a battery. So we have a positive side and a negative side, and that's huge. Because what we do is within this battery, we create a potential difference. And if we're thinking about kind of this gravitational and electric analogy, if we picture having like a proton at like the negative end of these parallel plates, or if we have a ball at the bottom of a gravitational field, if we come in here and we apply a force over some displacement to lift up the charge to move it closer to the positive plate, or to move the ball up further in the gravitational field, we know what we do is by forcing it over that displacement, we do work on that either charged particle or particle with mass. And from doing that work, we're putting energy into that system. And now the charged particle and the mass, in both these kind of analogous situations, they have this potential energy now. So they have this potential energy. In the gravitational case, you would have to come in and do the forcing. You'd have to force it up and lift it to get it up there. In the case of electric fields and with electric charges inside of a battery, this energy is actually coming from chemical energy. So we're taking chemical energy, it's doing work on our charges, and this chemical energy is transferred to electric potential energy, which is cool. So now we have these charges that are up by our top plate, and they have this energy, they have this stored energy, and we're thinking, hey, we can do something with this. So instead of just referencing how much energy, one particle gains some energy, but instead of talking about like one charged particle, what we want to do is kind of keep it more general, like we did with electric field and electric potential. We want to talk about this in terms of, hey, how much could we do? How much could happen based on the amount of charge? So instead of referencing how much energy that one charge gained, let's just talk about how much a charge would potentially gain if it weren't put in this situation. So we don't know like how much charge is moving, so we want to keep it general. And that's what voltage does. So electric potential or voltage is going to be this measurement of how much potential energy could we potentially have, instead of saying, hey, this one particle has this much potential energy. So we're going to say, hey, by moving it from the negative to the positive, by having this distance between the negative plate and the positive plate, there's a potential difference there, which will give energy to our particles based on how much charge those particles have. So then sometimes we use this terminology, sometimes. I never really talked about it. I was like, whatever, they're the same thing. But so we say we kind of have this thing that's forcing our charged particle up from the negative plate to the positive plate. So we think of this thing that's kind of doing this forcing. And when we have a battery that's kind of doing this forcing, we're going to say that that's called, we can call the voltage there, we can call it the EMF. It's kind of this fancy E as its symbol. And EMF just stands for electromotive force, and it's the same thing as the voltage of a battery. The reason I don't like defining it is because the name is kind of weird. It's not actually a force. It's just another measurement of voltage. So it's not a force, it's just a potential. It's just a voltage. So it's just voltage inside of a battery, but if you see the term EMF, just know it just means the voltage. It's not a force, it's a voltage. And so now we're saying, hey, we have all these charges with electric potential energy. We have, at this situation, at this top plate, we have charges with this electric potential energy. So what happens? What can we do with these charges with electric potential energy? And we know that they're not going to move back to the field. They're not going to move um, they won't move that way. We place them up there. We have this EMF that's kind of forcing them to stay at the top, so they won't move backwards through the field. So we've created this separation, and these charges all have this energy. So now they want to do something. They want to go somewhere. They want to do work on some sort of system. They want to get rid of that energy. So all we have to do is give them a path. And pretty much giving these charged particles with electric potential energy a path, that's kind of how the whole world runs now. This is electricity. This is how we make electricity. So I made this slide and I thought it was so funny, and then it's not really. But we can use this electric potential energy. We can use it to heat up stuff. We can run TV. We can get light. We can power our cell phones. We can go slot car racing. We can use this electric energy. We can use it to do so many things. And so we have all these charged particles that are stored up, and they want to move. They want to go from an area of higher potential to an area of lower potential. So this movement of electrons is what we're going to call current. We see here, this is a really nice model. I really like this idea because the electrons themselves, they're not like physically, like we're not leaving an area of no electrons. We just have this kind of general flow, this kind of general path for an electron to move. So we're going to measure this current as how much charge is passing a certain spot per second. So an equation for current that we may see is our current is equal to our change in charge over our change in time. So how much charge we have flowing over some amount of time. And then, so if we're thinking about electron flow, this is kind of a diagram of sometimes how I think we may think about electricity or current. Those electrons, these blue circles, they are not physically moving. They're just kind of, we have this general flow through it, right? So we have this general flow, but we're not leaving areas of no electrons. The electrons are replaced like we see in this situation. So we're not leaving areas of no electrons. We don't run out of electrons. We still have electrons that are replenishing it. Now we just haven't kind of established this potential difference, and there's a direction to our flow now. And then this is one thing that is very confusing. I think this is a really weird kind of convention that we set. I understand why we set this convention, but it's very confusing. So we kind of say, okay, well, electrons are the thing that can move. Like if we think about this, protons are bound to where they are. Electrons are the thing that can move. But when we talk about current, when they talk about current, like in most situations and kind of professional situations, we're going to actually think about current as a flow of protons. So I kind of made this diagram. I don't know if it's helpful, but we know that electrons are the things that can move. And when we move the electrons, we're kind of leaving behind, again, we're not leaving them behind, but this is just to help us out, to help us think about it. We're kind of leaving behind these protons. So by having these electrons move to the right, it's almost as if we have these protons moving to the left. So we're saying, hey, our current in this case is kind of flowing to the left. Our current, the way that we're going to use conventionally is to say that the current's going to the left. We're going to think about it as this movement of positive charges. And that's really just based on this convention. When we talked about setting up electric fields and talking about potential, we said, hey, what would happen if we had a positive test charge? And that's why we're using positive charges, or the flow of positive charge for current, because we established our system for electric field and electric potential based on the positive charges. So you don't have to really know this, but it just makes things a little bit easier moving forward conceptually, like, hey, what's going on? Why are we talking about this happening? That's not what happens. So yeah, it's not what happens, but conventionally this is going to help us out. So then we said, okay, well, we know that positive charges are going to go from an area of higher potential to lower potential. When we think about those topographic maps, we have to put energy in to move it up to a higher potential or a higher height. And then once it gets there, it's able to roll down and kind of use that energy, turn it into kinetic energy if we're thinking about gravity, or turn it into a different kind of energy if we're thinking about electricity. But so if we have these positive particles that are at a high potential, if we give them a path, if we give them a route, we can have them go from positive to negative potential, or higher potential to lower potential. So that current is going to flow from higher potential to lower potential. And this, again, is kind of us coming back to our model. We have these positive charges that are up here on this positive, this higher potential, because we did that work on them. We gave them this electric potential energy. We moved them against the electric field from low potential to high potential. So we gave them that electric potential energy, and now they're able to flow. So they flow from higher to lower. Again, positive charges aren't actually moving, but we're using this convention because it works with what we've set up. So yeah. And then now we want to think, let me just make sure it helps our model. We gave the positive charges, positive. Yeah, okay, cool. So then if we're thinking about like, hey, when we're connecting it, why are we using a wire? Why is it metal? Why does that let the charge move? So what we're going to say is that all objects have this quantity associated with them called a resistance. And this resistance is kind of unique to how an object is set up and what material that object is made out of. And the resistance, I have tea here and I almost spilled it. The resistance is just going to be a measurement of how difficult it is to push charges through an object. That's kind of the most basic way we can think about resistance. And so if we're thinking about like, hey, what factors affect resistance? It's cool because it kind of fits with what we would expect. So if we think about these two objects, object A or B, which one would be harder to move charge through? Well, we look at that and we say, well, it would be B. It's longer. It'd be harder to push. You'd have to do more pushing. So we have this idea right here that, hey, if the length goes up, our resistance is going to go up. And then if we look at these two objects, one that has a large area and one that has a small area, if we were trying to move charges through there, it'd be a lot easier if it had a larger area. We'd have more space to do our pushing. We'd be able to push more through there. With A, we'd get some like traffic jams. But with B, we have so many lanes we can flow really easily. So we have this other idea that as the area goes up, our resistance is going to go down. And then we also have this property called the resistivity, which is a property of material that describes the material's ability to resist current flow. So if we have a lower resistivity, we have a lower resistance. And this is kind of an explanation of why we use copper wires, why we use wires made out of metal instead of like air or something weird, I don't know. But so copper has a resistivity value of 1.7 times 10 to the negative 8th ohms per meter, whereas something like that we think of as being like conventionally conductive, like salt water, has a resistivity of 0.22 ohms per meter. So we see, hey, copper has a really, really low resistivity. Current can flow through there really easily. So we're going to say, okay, resistivity, property of the material. That's why we have copper wire. So this is dumb, but I like it. Here's a quick little simulation that just shows us, okay, resistivity is this little junk in there, how many atoms we have that are just kind of chilling. So if this goes up, our resistivity goes up, or our resistance goes up, sorry. If our length increases, our resistance goes up. And if our area increases, then our resistance goes down. So whatever. All right, but yeah. So if we're looking at this resistance and its relationship to other variables that we're going to talk about, specifically current, we said, okay, well, this is our equation for resistance, but the resistance is just going to be a measurement of how difficult it is to move current through an object. So if we establish some sort of potential difference across a wire, like we were just talking about by having this separation of charges, the amount of current will be determined by the resistance. So resistance is how able are we to move current through this wire. So the amount of current is going to be based on the resistance. So we have this idea that current and resistance have this inverse relationship because we said, hey, this is our definition of resistance. If we have a high resistance, we won't be able to easily get current through this wire. If we have a low resistance, we'll easily be able to get current through this wire. And this relationship that we see, we're saying, hey, if we have some sort of constant potential difference, I and R are inversely related to each other. This relationship is called Ohm's Law. And this is kind of our main idea where we can calculate a lot of things and stuff about circuits with this Ohm's Law, this V equals IR, or the way that it's stylized on the equation sheet, I equals V over R. And then, so that's Ohm's Law. And one thing that's weird about Ohm's Law is that it's not actually like a physical law. You can reference it on the like AP test and you can say, oh yeah, stuff follows Ohm's Law. But there's a few objects that don't follow Ohm's Law, so we can't say, hey, this is a law. So there's going to be two different types of objects. There's going to be ohmic objects and non-ohmic objects. So if we analyze an object and we look at V, we look at I, and we look at R, and this Ohm's Law holds, if we see, oh, V equals I times R for this situation, then we're going to say, hey, this is an ohmic object. It follows Ohm's Law. If we analyze an object and say, oh, well, Ohm's Law is not holding here, V does not equal IR, then we can say, oh, well, this is a non-ohmic material. So for example, like an example of that is a battery is going to be non-ohmic. In a perfect battery, we're going to say there's no resistance in it and there's no current flowing through it. So we can't calculate the potential difference by saying V equals IR. That doesn't work, right? I and R are just, they're nothing. So we can't find the potential difference in a battery by using Ohm's law. So we can say that it's non-ohmic, it doesn't follow Ohm's law. And the potential difference in this case is really created by the separation of chemicals instead of the current flow and resistance. So that's just a quick little example. I don't know if it'll ask about that, but whatever. And then so we're saying, okay, properties or materials have this property called resistance. When we think about resistance, that sounds kind of bad, right? Like resistance doesn't sound like something that we want. It sounds like a negative property of materials. We wouldn't want resistance. We'd want everything to go fine. But resistance is not necessarily bad. We can use it to our advantage and really kind of harness this energy from it. So we said, okay, well, these particles are going to have this electric potential energy. These charged particles, when they're coming out of a battery, will have electric potential energy. We can actually use that electric potential energy through this resistance. We can have energy flowing from charges to the wire, and we can use this electric potential energy as thermal energy. Like here's an example of a toaster up here. We're taking energy, this electric potential energy, and through resistance, we're turning it into thermal energy. Or if we say, hey, like I'm constructing this circuit, I need a perfect amount of current through this element, and I need a perfect voltage here, we can use resistors to change the amount of current or voltage that we're getting in that circuit and then really deliver the perfect amounts. That's another use for these resistors. Or we can create light. We can say, hey, let's transform this electric potential energy to thermal energy, and then that transforms into light energy. So resistance is actually good sometimes. It's not necessarily a bad thing. So what we said is, okay, these charges have this electric potential energy. There's this potential between these batteries, or between the terminals of the battery. So if a charge is brought in there, that charge will have electric potential energy that is related to the amount of potential between those two terminals. So like we were saying before, they use this electric potential energy and they can transform it into other types of energy. And then by the time the charge is going to end up, or the time the current is going to go from the positive terminal to the negative terminal, it's going to have used up all of that energy. So that's kind of a really big idea. It has this potential energy, and then by the time it gets back to 0 volts, it has to have 0 volts, right? This voltage is a property of the location. So if we get back to that location, we have to have 0 volts. So we have to use it all up by the time we go from one to the other. So yeah, here's just a little whatever. So for an example, if we're thinking about a resistor, how does it actually use up energy? What's actually happening here? This picture is really small. I have a bigger picture on the next slide. But in a resistor, for example, we're saying, okay, there's potential difference on each side of the resistor, right? So we have this potential difference, this positive V on the top terminal of our battery, and then a 0 V on the bottom terminal of our battery. And because there's no resistance in our wire, or we'll assume that there's no resistance in our wire, that means that the top plate of our resistor, the top side of our resistor, also has to have a potential of positive V, and this also has to have a potential of 0 V at the bottom, because again, there's no voltage drop in this wire, because it's going to be a perfect wire. So we're saying, okay, there's a potential difference on each side of the resistor because it's hooked up to this battery. And because we have this potential difference, it means that there's an electric field between the ends of the resistor. We have a positive V, 0 V. There's going to be an electric field pointing from positive to negative. And we know that when charged particles enter an electric field, they're going to accelerate. So we have this particle that's moving kind of slowly, then it's going to accelerate. It's going to go from positive V to 0 V, so it has this electric potential energy, and then that energy is going to be converted to kinetic energy. This particle is going to speed up. It's going to be moving faster as it goes through this electric field, just like how objects are going to speed up in a gravitational field. And then we say, okay, well, this charged particle's electric potential energy is transformed to kinetic, and then while it's moving down, it's going to collide with atoms in the resistor. And that's going to transform it to thermal energy. When we have these collisions, these objects will gain the kinetic energy. These atoms will start to vibrate more. They'll have more thermal energy. So in this case, we had this electric potential energy at the beginning, and we've used it all up by the time we get to the end of the resistor. So here's just a little bigger picture of that. We see, okay, here's our charged particle. It has this electric potential energy. As it goes down this electric field, it speeds up, has this kinetic energy, and then collides with the atoms in here and turns that into thermal energy. So it's kind of cool. We're saying, oh, we're using this energy, we're turning it into something. Okay, and then, yeah, like I said before, we're going to have this assumption that the resistance in a wire is so low that there's no potential difference. So the potential from here, we can think about this wire as not even existing. It's just kind of a way for us to move the charge from one to the other. But yeah. All right, so then when we're thinking about resistors, we can set up really any configuration of resistors that we want to get the values of voltage and current that we want. And there's really two ways that we can arrange circuit elements. We can either have them in series or we can have them in parallel. And we'll talk about what that means in a second. So series means we have them in a row. If we're thinking about current moving through these resistors, in series, they do not have a choice. If they go through this one, they have to go through the next one. There's no path that they can take to avoid them. That's kind of how we can think about series. There's one way that we can go. And if we're thinking about adding them up in series, what we're really doing is we're creating one long resistor. We're saying, oh, you have to go through here. The wire doesn't really do anything. So we're really just creating one long resistor. And we know that the resistance goes up with the length of an object. So in this case, what we see is, okay, if we're adding resistors in a row, what we have to do is we're saying, well, the resistance is going to go up. So if we're going to do this, I made you guys do the math before. We're not going to go over the math again. But so what you're really doing is saying, oh, well, we can add up the lengths, and then we're adding up the resistances effectively. So to find the total resistance of resistors in series, all we have to do is add up the resistance of each resistor in series. We have this equation that says R series is equal to the sum of all the resistors in our series. And then the resistance increases with length, so adding resistors in series is really just like creating one long resistor. And one main idea when we're dealing with series resistors, in a series configuration, the current through each resistor is the same. So again, the current has no choice. It has to go through one resistor, and then it has to go through the next because they're in a row and there's no other paths. So in series, the current through each resistor is the same. Now if we're looking at parallel, that's where we add them side by side. We're kind of giving this current a choice is a way that we can think about it. If we come here, we're the current, we're coming to the battery. Now we have a choice. We could either go through this one, or that one. So what we're doing here is effectively increasing the area. And we know that if the area goes up, our resistance is going to go down. We're giving more lanes. I think before we kind of used like a highway analogy. If you're on a single lane and there's like a stoppage, it takes a long time. There's a lot of resistance. But if there's multiple lanes, more cars can flow through. So if we're looking at parallel, it's effectively like adding them next to each other. We're giving the current this branching path. So there we go. The resistance decreases with area, so adding resistors in parallel is really just like creating one thick resistor. And then one thing that we can say is in a parallel configuration, the voltage drop through each resistor is the same. So if we think about having like a battery here, by the time we get to the end of each resistor, we have to be at the same voltage as the zero terminal on our battery. And then when we want to add them up, we have to add up the inverses. We have to say 1 over the total parallel resistance is equal to 1 over each of our individual resistances. We'll add those up and then take the inverse to find the total resistance. All right, so then just kind of some generalizations, some big conceptual things about circuits and setting up circuits. In general, I'm just going to say in general here because maybe there will be some weird situation like if you have a complex circuit. But in general, if we add a resistor to a circuit in series, we'll see that the total resistance will increase. And that will decrease the total current in our circuit. So if we add more in series, we're saying, okay, it's making it harder for the current to move. That's going to then increase the total resistance in general, which will then decrease the current because there's more resistance. In general, adding a resistor to the circuit in parallel will decrease the total resistance, and that will increase the total current. So that's just us following Ohm's law, this V equals IR. But if we add them in parallel, what we're doing is we're adding another branch. We're giving it another path that it can go through. So if it has more paths, there's going to be less resistance, just like the highway analogy we just talked about. If you think about a car in a single lane, it's going to be harder than if there's multiple lanes that it could drive in. So then we can say is, again, Ohm's law applies. So the total current in the circuit is going to be a property of the total resistance of the circuit. This V equals IR is going to apply for every single resistor inside the circuit. And if we kind of figure out the total resistance in the circuit, we can say the total voltage in the battery equals the total current times the total resistance. And then just a rule of thumb, this is something that's really conceptually weird, but if you change something about any of the resistors in the circuit, the total current will change. If you change anything, it'll change our total resistance, which will change our total current, but our voltage of the battery is going to stay the same. So then when we're trying to solve circuit questions, we can use two rules that are really going to help us out. One of them is going to be Kirchhoff's, however you say it, Kirchhoff's loop rule. And this is really just an expression of the conservation of energy, but it's this idea that all of the potential differences around any loop formed by the circuit must sum up to zero. We'll see an example of this in a minute. But it's really just, conservation of energy, saying the total energy in our system has to be accounted for. We don't add additional energy. Energy can't randomly disappear. And if we're thinking about it, voltage is just energy per charge. So if we put a set amount of charge into our system, we're just really comparing energies. So energy has to be conserved in our system. So if we're looking at this, we have this poorly drawn circuit. We say, okay, well, the battery has a potential difference of 9 volts. The negative terminal is at 0 volts. The positive terminal is at 9 volts. And then we can think, okay, well, over here, the wire is just going to kind of be an extension of our battery, which means that the top plate of this resistor has 9 volts, and the top plate of this resistor has 9 volts. And then I kind of went in and filled out corresponding values. So I said, okay, here we're dropping to 0. Here we drop to 3. Then again, the wire is just an extension, so these are going to both be at 3, and then both be at 0. I just kind of filled in those values and then made sure that they were right. But so now let's practice our loop rule. Let's look at this. So if we're looking at this case, we say, okay, well, any loop that we make will sum to a total voltage of 0 volts. So let's see. If I start at this end of the battery, I go from 0 to 9, so I have plus 9 volts. And then in this loop, I go plus 9 to 0, so I end up with negative 9 volts here. So I get plus 9 minus 9. That's a total of 0 volts. So that loop worked out. Let's look at another loop. So same thing, we're going through the battery. We're adding 9 volts because we're going through the battery. We're adding that energy. Over here, we go from 9 to 3, so that is minus 6 volts. Over here, we go from 3 to 0, so minus 3 volts. So overall, we went in that full loop, plus 9, minus 6, minus 3, 0 volts, checked out. Same thing if we take this branch of our circuit. I won't go through it, but it's the same thing. It's also going from 3 to 0. Then if we look at this case, again, we can use any loop. So it doesn't matter if it's connected to the battery or not. This is going to work for any loop that we look at. So in this case, I kind of came in here and I said, okay, well, which direction is the current flowing? So the current's going this way. So then just kind of one thing to note, if you're going against the flow of current, it's going to be negative. We can see why because we've labeled like the positive side and the 0 side, or the lower side. But if we didn't do that, what we'd have to think about is, well, if we go opposite, it's going to be positive. So in this case, we'd be working against it, so we'd be kind of like adding energy, because what the resistor is going to do is take energy away. So if we kind of reverse that process, instead of it taking energy away, we're going back to that state where we had energy. So we're kind of adding energy in here. So if we look at this case, we start at 0, then we add 9, so we have plus 9 volts. And then same thing here, minus 6, minus 3. Within that loop, we've ended up at 0. And now just kind of an example of a bad situation, a situation where the loop rule doesn't work out. We see how weird this is. If we start over here at 0 volts and then we add 9, okay, we've added 9 volts, 9 joules for every 1 coulomb of charge we put in here. And then we go through this loop. Let's say that this has a 12 volts over here and 0 volts over here. By the end, when we get to this loop, we have negative 3 volts. It's kind of weird. So what that says is, okay, we added 9, we took away 12, so we used 3 joules for every 1 coulomb that we put in there that we didn't have. We didn't have that 3, but we used it. So we're kind of in debt with 3 joules for every 1 coulomb. That doesn't make any sense. That doesn't satisfy conservation of energy. So that's no good. That's why our loop rule is great, because it's conservation of energy. That's all that it is. And then the other law that we have, the other rule, is Kirchhoff's Junction law or Junction rule. This one is one that we were much more comfortable with using, and it's really just this statement of conservation of charge, this idea that the amount of charge into our circuit has to equal the amount of charge out of our circuit. So if we ever come to a junction, if we split our wire into two or more paths, we're going to call that a junction. Whenever we come to a junction, we see that the total current into our junction has to equal the total current coming out of our junction, because we're not creating or destroying charge. In this case, we're saying, okay, we have 10 amps going into our junction. We split into two ways. We have 4 amps over there, 6 amps over there. Great. We sent 10 amps in. We got 10 amps out. In this case, we're saying, okay, well, we got 10 amps in. We'll have 8 amps over here, then 6 amps over there. That's weird. We put in 10. We got out, what, 14? Yeah, I know how to do math. 14 amps. Where'd the extra 4 amps come from? That doesn't make any sense. So whenever we're analyzing circuits, these rules are all going to have to apply. The loop rule, the junction rule, and Ohm's law. Using these 3 rules, we can pretty much figure out anything about any circuit, no matter how complicated it is. Speaking of complicated circuits, sometimes what we may see, I don't know if we'll do it on the AP test, I doubt it because it takes a lot of time, but just in case, covering the bases, sometimes we may have complex circuits, so we won't see like just 2 things directly in series or 2 things directly in parallel. They'll be messy and they'll be weird. But what we have to do in that case is just kind of break our circuit into pieces. What we can do is find the equivalent resistance between resistors that are directly in series or in parallel. So that just means kind of finding the total between them. And we'll keep on going until we have one equivalent resistor. I went ahead and did one. I doubt they'll have you do this on the AP test. I think that'd be really weird. But just to kind of see what happened, we said, okay, well, we have this complicated resistor, or this complex circuit. It's complicated, but let's just kind of find the pieces that we can add up, find the spots where we can find the equivalent resistance. I see right here that this 33 ohm and 61 ohm resistor are directly in series with each other. So I can say, well, I know how to add things in series. I can just add up their resistances and find the total resistance there. I've kind of turned those 2 resistors into 1. And then I can do the next thing. I can say, well, here I have 2 that are directly in parallel with each other. I can kind of combine those. I can find the total resistance between those resistors in parallel, turn it into 1 resistor. So I do that. I compress them down into 1 resistor with an equivalent resistance. And then I say, oh, well, now this one and that one, those are directly in series with each other. Okay, well, I know how to do that. I know how to find the total equivalent resistance between those 2. I can just add them up. And now I've added them up. I have an equivalent resistance between them. And now I have 2 that are in parallel with each other. I can find the equivalent resistance between those 2 in parallel, turn them into 1 equivalent resistor. Now I have 2 in series, and by following that process, I can find the total resistance, the total equivalent resistance in the circuit. If I know the voltage of the battery, I know the total V, I know the total R, I can find the total current. And you're probably thinking, it's probably the main idea on your mind, okay, we use energy when we go through these resistors or go through a circuit element, but can we store energy in our circuit? Wouldn't that be cool? So you can store energy in your circuit. You're going to store it in the form of a capacitor. So capacitors have this ability to store charge and then therefore store energy in the electric field, which is kind of weird. But so what a capacitor is, we talked about it. We'll kind of talk about how we can hook one up, how we can make this work, and how it stores energy. But so the first thing that we'll do is we'll take our capacitor. Here we're going to model it as 2 parallel plates. That's how we're usually going to see it. We'll hook it up to the battery. And we'll say, okay, well, the battery had this positive terminal and this negative terminal. And yeah, these charges, they're kind of chilling in here. They don't want to be super next to each other. So we've given them this chance to flow to go to a lower potential. So they're going to do that. Current will begin to flow away from the positive terminal. And based on this convention, again, we're saying that the positive charges is the one that's moving. Technically, that's not right, but it's the convention that we're using because it works with field and potential. But so these positive charges will begin to flow. So they're moving away. Protons are moving. And charge will begin to flow away from the positive terminal based on our convention. Positive charge is moving. And we'll say that these positive charges will begin to bunch up on this top plate. They can't physically move through the air. That would be weird if charges could just jump through the air. Then none of our circuits would work. But in this case, we're saying, okay, well, the positive charges, they'll stay on this top plate. They've gone as far as they can go, and then they won't be able to go any further. But while they bunch up on this top plate, what's going to happen is that they'll repel the negative charges, they'll repel the positive charges on the bottom plate. We know that like charges are going to repel each other, So we have a bunch of positive charges on this plate, and they'll say, well, I am too close to other positive charges. I don't like being there. I'm going to go to a spot that's a little bit better, a little bit less positive charges. So those positive charges will move away, which will leave electrons, will leave negative charges. So now we have a positive plate and a positive top plate and a negative bottom plate. And if you think about when will this stop, that sounds like it's like a bad thing. Like, when's it gonna stop? It'll just stop when the energy of the battery is equivalent to the energy stored between these plates, or when the voltage of the battery is equal to the potential difference of the capacitor. I'm going to say that one more time, but keep the same thing. When the potential difference of the battery equals the potential difference of the capacitor. Because really, again, we're just storing energy here. We can't store more than the battery has. That would be weird. That would break conservation of energy. So then, afterwards, we're saying, oh, well, we can store this energy in the capacitor, or we can store this charge, which is then storing energy in the field, but we can store it, and then we can use it just like a battery. So we can say, oh, well, if we wanted to, we could take the battery away. The energy would still be stored because we still have this difference in charge in the plates. So this energy is stored. We could hook it up to different elements of circuits. Like we could hook it up to a light bulb here. This is kind of our symbol for a light bulb. And now it's acting just like a battery does. It has this positive plate. It has this negative plate. And what will happen is we've given them a path so they can kind of seek each other out. We know that the positive will attract the negative. They want to go by each other, and they kind of want to come back to the spot to lower their potential. Right now we have the potential difference. It doesn't want that. So these protons, these positive charges, they'll move just like what we see in a battery. So they'll flow, and they'll be able to flow through these circuit elements and provide this current. It won't be sustained. It'll only happen until we've kind of rebalanced out and reshuffled anything. But we can use this energy just like we do with a battery. And then we're thinking, okay, well, that's cool that we can store this energy, we can store this charge. What factors are going to affect this thing's ability to store charge? So, or in other words, what's going to affect the capacitance? So what we can say is, well, it's really based on these parallel plates. If we have larger plates, we'll be able to store more charge. There will be more spots for us to store charge. If the plates are closer together, we'll also be able to store more charge because the effect of one being by the other one will be stronger, because we know that we have this Coulomb's law that says F equals KQ1 Q2 over R squared. So the closer they are to each other, the more of a force they'll have to move away the other charges. And then if there's something between the plates, this is also going to affect the ability to store charge. If we put something between the plates, we're going to call this a dielectric. And one thing to know when we're thinking about this, energy stored in the electric field, and we'll kind of look at this dielectric really quick. So typically what we're going to say is, well, let's just assume that we have a vacuum between the plates. So there's no air, there's nothing, it's just a vacuum. And when we do this, we'll have the charges on the top plate, the negative charges on the bottom plate, and this creates a potential difference. We'll have positive and negative, and when we have this potential difference, we know that there's going to be an electric field between them. So there will be an electric field that points from the positive plate to the negative plate. And if this is happening in a vacuum, we're going to have a constant of just this epsilon naught. This epsilon naught stands for the electric permittivity, which just tells us pretty much it's just a measurement of how easy is it to create an electric field inside of a vacuum. I think I say that in a second. But then what we can do is sometimes maybe we're feeling a little crazy. We want to put something in between these plates. And the thing that we'll put in between them is called a dielectric. And this will actually weaken the electric field, and we'll look at that now. But if we wanted to kind of quantify it, we'd say, well, epsilon naught is telling us how easy it is to create an electric field in a vacuum. This kappa right here is kind of a coefficient for that. It's telling us, okay, well, we have this much difficulty for a vacuum. Let's change it by some factor. That's what the dielectric constant does. So if we're kind of zooming in, this is me looking at the particles inside, the atoms inside of the dielectric. What we can say is, well, we know that it's an insulator because the charges are kind of staying. But so it's an insulator, and we know that it has protons and electrons inside of it. So we have this exterior field that's kind of pointing downwards that will move the electrons in here. That now we're going to say that the protons stay where they are just because it works out for us. But so the protons are staying where they are, and we know that the negative charges will move in the opposite direction of the electric field. So we'll see the situation where the negative electrons inside of the insulator, they're able to kind of shift a little bit, and they're going to be able to align themselves in the opposite direction of the electric field. They'll kind of point, they'll go to the top side because we have this positive plate there, and they're attracted to the positive one. So electrons in the dielectric will move in accordance with the electric field, and this is actually polarizing this dielectric. And what's weird is it's creating its own electric field inside there. Now we have this situation here where we have a slight negative charge on the top and then a slight positive charge on the bottom. So we've created this oppositely directioned electric field from an electric field. That's weird. But so if we're thinking about this now, the net electric field between these plates has actually weakened. Before we kind of thought about, okay, we have this total positive downwards electric field, and then this oppositely pointing electric field from the dielectric. So our net electric field, it's weakened. Technically, this is not like a great drawing because I showed it as like a vector, but still it'll be uniform between these plates. It'll just have a weaker value. Okay, so I drew it like it stops here. It doesn't stop here. The electric field is still constant from the top plate to the bottom plate. It doesn't stop. It's not gone. But I just wanted to show, hey, the magnitude is less. So then this is the weirdest part. This is a part that I'm still struggling with a little bit. But so the electric field is weakened. We talked about before that we have this equation that tells us the potential difference equals the electric field times the distance between these two things. So if we weaken the electric field, we've also weakened the potential difference. And we have this equation that says, well, our capacitance is related to charge and potential difference by just saying the potential difference is how much charge we can store per capacitance. So we're storing the same amount of charge with the lower potential difference. So our capacitance actually went up. If we're thinking, if we kind of rearrange this capacitance as charge per potential difference, we're storing the same amount of charge with a lower potential difference, so capacitance actually went up. So then if we're looking at this equation, we have this idea that the capacitance is equal to this dielectric constant times epsilon naught times the area divided by d, the distance between these plates. And yeah, kind of a weird idea. But so yeah, the larger the constant, the higher the capacitance. And for a vacuum, kappa is just equal to 1. And I don't know, I'm hesitating because I thought I put this link in here, but I didn't. But so yeah, we have this idea. If we kind of look at here, we can say, okay, if we move these closer to each other, we can store more charge. Further away, the field weakens, we can store less charge. If we have less area, we can store less charge. More area, more charge. I didn't put that in there apparently, my bad. All right, but then yeah, so then if we think about, we can put capacitors in our circuit, just like we did with resistors. We can put them in series. So if we add capacitors in series, what we're effectively doing is increasing the distance between these two plates. Excuse me, sorry. So we can say, okay, well, we're effectively increasing D, which means that these are inversely related, so capacitance is going to go down. Then one little thing to note is that if these capacitors are in series with each other, they have the same amount of charge on each one. So we'd have like a positive Q, let's say, I don't know, 5 coulombs. We'd have positive 5 coulombs stored on this charge, or on this plate, which would then induce a negative 5 coulomb charge on this one, right? Because we'd scare away 5 coulombs from this plate. So we've scared away those 5, or forced away those 5 coulombs, positive 5 coulombs. They have to go somewhere. So they're going to go to this plate. So this 5 coulombs will go to that plate, which will then scare away positive 5 coulombs from the bottom plate. So in series, the plates are going to have the same amount of charge. Each capacitor is going to have the same charge. If we're doing it in parallel, if we're adding capacitors in parallel, this is supposed to say parallel. So if we add capacitors in parallel, what we're doing is we are effectively increasing the area of our plates. We're saying, well, if we kind of combine these two, now we have plates with larger areas. And we see, okay, well, the area is directly related to the capacitance. So if our area goes up, our capacitance goes up. Our ability to store charge has increased. And then we can say the same thing that we did with resistors. If our capacitors are in parallel with each other, there's the same voltage drop between each capacitor. So this is, again, in accordance with Kirchhoff's loop rule. Still has to apply, still has to hold. Oh, there now is where I put it in. No, just kidding. This is a video. So then one of the things that they're going to ask us about, probably most likely, is if we put capacitors in a circuit. So when we're thinking about capacitors in a circuit, immediately when the capacitor is connected to a circuit, the capacitor is going to act like a wire. The charge, there's not that much difference between them. The charge can really easily make charges across the plate move. So it's just kind of this direct, okay, we bring a proton, the electron's like, oh, okay, I don't like that, and then move away. So immediately it acts like a wire. It acts like there's nothing there. We can think about it as just a wire. After a long amount of time, though, the capacitor is going to act like a break in the circuit. We're going to say, okay, these plates are full of charge. The voltage of the battery is now equal to the voltage of the capacitor. We've maxed out our energy. We've satisfied conservation of energy. We're not making more energy. So we're kind of at this state where the energy is stored in the field because of this separation of charge in the capacitor. So we've reached the maximum amount of charge that we're going to get. So we've satisfied conservation of energy. We're storing it. And nothing else is going to move because we've kind of reached this maximum energy state for our circuit. So after a long time, the capacitor acts like a break in the circuit. And then just a little thing, if we are analyzing circuits with capacitors, the loop rule still applies. And I really quickly want to show you this video. I think Clay showed it to me. Actually, I don't remember. I think it was Clay. Early on when we were doing capacitors, I just think this is a very helpful visual. So first we see, okay, we're charging the capacitor. I think this is charging. Yeah, we're charging the capacitor. We're hooking it up. So after a short amount of time, right when we're kind of hooking it up, we see, okay, we move this charge and it directly moves the other charge. So it's acting just like a wire would. Again, it's acting like a wire. The charge is pushing a charge from the other plate. So the charge is not flowing through the plate. It's just kind of forcing a charge from the other plate. Then over time, we see, okay, this gets slower and slower. There's a bit more forces. We don't have to worry about these intermediate steps. But then we move that last one, and we've kind of moved all the charge that we can, and we won't have this movement anymore. And then afterwards, let's see, is this discharging? No. Oh, whatever. Okay, but yeah, so cool. And then, okay, I think I just have quick little examples and we're good to go. But yeah, so if we're looking at this situation, if we want to figure out after a long amount of time how much voltage is stored, or what's the potential difference between these plates of the capacitor, it's pretty easy to do. We can just use the loop rule. We can say, well, after a long amount of time, we can say there's no more current in our resistor, no more current throughout our circuit. So if we tried to do Ohm's law on this resistor, we'd say, well, V equals I times R, but I is just equal to 0. So the potential difference across this resistor after a long time is 0. And then we can do the loop rule. We can say, okay, well, we have a positive 9 volts from the battery, a 0 voltage drop from this resistor, and then some voltage drop from the capacitor. We know it would have to be 9 to satisfy the loop rule. Sometimes this gets a little bit more complicated. We have a situation like here, we'd say, okay, well, let's have a resistor that is in series with a capacitor and a resistor that are in parallel with each other. If we're looking at this case, well, after a long amount of time, the capacitor acts like a break in the circuit, but that's just breaking off this branch. That's just closing off this branch with the capacitor in it. Current can still flow around here. It can still flow from this resistor to that resistor. So that's a situation where it gets a little bit more complicated. We'll still have a potential difference across this capacitor, but it won't be equal to the potential difference of the battery, right? Because we kind of have this we'll still have a potential drop from this resistor here. So it's a little bit more of a complex situation, something to think about, something that if there is a circuit question, I wouldn't be surprised if they asked about, but who knows? I don't know anything. It sounds like I know something I don't. That's just my speculation. And then finally, we know that we're saying, okay, we're storing energy in this capacitor. Technically, we're storing energy in the electric field between the capacitor, between the plates, but we can think about storing energy, having this potential energy within the capacitor. The way we can find that is just doing 1/2 times the charge times the potential difference, which is the same as saying 1/2 C times the potential difference squared, because we have this equation way back here that the potential difference across the capacitor is just Q divided by C, the capacitance. And yeah, that's kind of what I have for circuits. Hopefully that was kind of helpful.